In this presentation, I consider the uptake of binary mixtures within zeolite crystals. In particular, I wish to demonstrate that the faster diffusing component may experience transient overshoots during the equilibration process. And the occurrence of transient overshoots and attainment of supra-equilibrium loadings within the zeolite crystals can be modeled using the Maxwell-Stefan diffusion equations. See also two other presentations of mine on my YouTube channel. In this one, diffusion in ordered crystalline microporous materials, I describe how the Maxwell-Stefan diffusion equations can be set up. And in the second presentation on transient breakthrough simulations, I discuss the methodology for performing simulations of transient uptakes and breakthroughs in fixed bed adsorbers. The Maxwell-Stefan diffusion equations recognize that the chemical potential gradients are the proper driving forces for diffusion. The chemical potential of any species is relatable to the partial fugacities in the gaseous phase, and the partial fugacities in the gaseous phase are relatable to the molar loadings inside the crystallites of the adsorbent by use of the IAST for thermodynamic equilibrium, along with the data on the unary isotherms. Therefore, the relation between the chemical potential gradients and the gradients of the molar loadings are via a matrix of thermodynamic factors, gamma ij. For a binary system, we have a matrix of thermodynamic factors with 4 elements. The cross coefficients gamma 12 and gamma 21 are non-zero in general, and the non-zero values of gamma 12 and gamma 21 account for thermodynamic coupling, in which the fluxes of any component cannot be related only to its own gradient. Rather, the flux of any component is dictated by the gradients of all components in the mixture. Thermodynamic coupling effects are of vital importance for kinetic separations, as we shall demonstrate in subsequent slides. Ignoring thermodynamic coupling effects, in other words, assuming that the cross coefficients of the thermodynamic correction factors are 0, may lead to significant errors in the transient breakthrough simulations. In order to demonstrate the importance of thermodynamic coupling effects in kinetic separations, let's take the specific example of purification of natural gas. In several natural gas resources, the concentration of nitrogen that is present can range up to 20%. Now, since the nitrogen that is present in the gas lowers the heating value, the pipeline specification for transportation of natural gas specify that the nitrogen content should be less than 3%. One technological solution for reducing the nitrogen content from 20 to 3 is to use pressure swing adsorption technology, which with an adsorbent that is selective to nitrogen, so that methane can be rejected into the gas phase and recovered at the required purity. However, all available adsorbents are selective to methane because of the higher polarizability of methane with respect to nitrogen. The solution, therefore, is to rely on diffusion selectivity by choosing, say, an adsorbent such as LTA4A zeolite. LTA stands for Linde type A, and 4A zeolite contains 96 extra framework cations per unit cell. The location of these cations are shown by the blue spheres. Note also that some of the cations are located in the window region, hindering the transport of guest molecules from one cage to the adjoining cage. The cage diameters of LTA4A zeolite are approximately 11 angstrom, and the dimension of the window aperture is about 4 angstrom. Let's have a look at the animation to see how methane hops from one cage to the adjacent cage. The hopping is one molecule at a time, and therefore the molecular hops are uncorrelated. Nitrogen also hops one molecule at a time across the windows, and the hopping is in a lengthwise direction. Since the cross-sectional dimension of nitrogen is 3.3 angstroms, that is significantly lower than the diameter of the methane molecule, the diffusivity of nitrogen inside LTA4 zeolite is about a factor 25. And this is the basis of the kinetic separation of nitrogen-methane mixtures. Habgood in 1958 published a set of experimental data on transient uptake of nitrogen and methane in LTA4A zeolite at a temperature of 194 Kelvin. The data is remarkable in that it shows that the nitrogen uptake shows an overshoot in the molar loading, and the value of the peak is about 2.2 moles per kilogram, significantly higher than the value at equilibrium, which is 1.2 moles per kilogram. The uptake of methane, on the other hand, is monotonic, and the component loadings approach its equilibrium value in a monotonic manner. The attainment of supra-equilibrium loadings of nitrogen and transient overshoots are signatures of kinetic separations. Let's model the nitrogen-methane mixture uptake in LTA4A zeolite using the Maxwell-Stefan diffusion equations. The D12 term signifying correlations between 1 and 2 need not be accounted for because the guest molecules jump one at a time across the windows from one cage to the adjacent cage of LTA4A zeolite. We take the diffusivity values based on the data provided by Habgood, and let's first consider the transient uptake simulations in which the thermodynamic coupling effects are duly accounted for. The uptake of nitrogen is plotted, is followed here as it develops inside the crystallite of 4A zeolite. This is the surface of the zeolite, which is in equilibrium with the bulk gas mixture. This is the center of the crystallite. The nitrogen, shown by loadings in moles per kilogram, shown by these red lines. Note that this is the loading at the surface, and the peak loading is significantly higher, and it diffuses much faster than methane. And at this time, the maximum loading has been achieved, and the loading inside the crystal of nitrogen decreases finally to reach the value at equilibrium. So it undergoes overshoots as observed in the experiments. Let's now perform the same set of simulations, but now ignoring thermodynamic coupling and assuming that the matrix of thermodynamic correction factors is the identity matrix. In other words, gamma ij is the Kronecker delta. These simulations are shown here. Again, this is the surface of the crystallite. This is the center. The red line is for nitrogen. The blue lines are for methane. Nitrogen penetrates faster into these central regions, but you will note that no overshoot has been experienced so far by nitrogen. Methane is tardier in its uptake and takes a significantly longer time to reach equilibrium. Let us examine the experimental data for transient uptake of carbon dioxide and ethane in the ratio of 60 to 20 inside a DDR zeolite that consists of cages separated by windows that are 3.7 in this direction, 3.7 angstrom, and 4.4 angstrom in this direction. It's 8-ring window. CO2 diffuses faster than C2H6 because the cross-sectional dimension of CO2 is significantly lower than that of ethane. The experimental data from this publication shows that the transient uptake exhibits an overshoot in the loading of CO2 before it equilibrates to a value of 0.6 moles per kilogram. Ethane is the most strongly adsorbed component, but has a lower diffusivity. Its approach to thermodynamic equilibrium is monotonous. Let's consider the modeling of the 60-20 CO2 ethane uptake in order to compare with the experimental data. The Maxwell-Stefan equations are shown here. The correlation term can be neglected because each of these gas molecules jump across the windows from one cage to the adjacent cage one at a time, and the intercage jumps are uncorrelated. The experimental data can be matched by taking the diffusivities as shown in this. Let's have a first look at the transient uptake in which thermodynamic coupling effects are duly accounted for. the CO2 experiences an overshoot above the value at the surface, and as time progresses, the loadings of CO2 in the crystal decreases to reach equilibrium. If thermodynamic coupling effects are ignored, the transient uptake is shown here, where the uptake of nitrogen and methane are both monotonous.